All right, welcome back to our new playlist of Kalman filter theory and applications, equation drill down. So in the last playlist, we went through a heuristic introduction, an intuitive introduction to the Kalman filter concept and algorithm. In this playlist, we're going to drill down on the real equations and get into the gory mathematical details. And then in the next playlist, we're going to have a drill down in the area of state space concepts and state dynamics in particular. So in this playlist, we're going to have at least 5, perhaps more videos. But this first one is going to be dealing with the mathematical formulation of the problem and some indication of the form of the solution for the Kalman gain. But it won't be the full story just yet. So in the next video, we'll have a drill down on the state dynamics and the covariance extrapolation equations. And then finally, we'll add the covariance update and the state update equations, the Kalman gain, and present what I refer to as the 5 fundamental Kalman filter equations. And then we'll have a video with several examples, 3 examples I've worked up together with Python code that you can find out on GitHub. If you go to the GitHub repository URL that was indicated in the splash slide to this video, that'll take you there to where the Python scripts are. And then after that, we'll have some videos on exercises. Okay, so let's dive into it. What is the Kalman filter problem? Well, at a high level, we're saying we've got 2 models. One for the model of how the state changes with respect to time, and a second one about how we observe the states. Now, we might not be able to observe all the states. The state is typically a vector process, so there's plenty of states there. We might only be able to measure 1 or 2 of them. So not having full observability into the state vector itself requires that we have a measurement model that tells us how the measurements are related to the state. And then once we have those 2 models, we want to find a way to optimally combine our knowledge of the predicted state estimate with our knowledge of the actual measurement, and then produce an updated state estimate. Now, it's from the state dynamics model that we get the predicted state estimate, and it's from the measurement model that we get the measurement information. And so combining those 2 things uses all the information at our disposal in order to come up with an optimal estimate of the state. So the goal here is to find an optimal gain with which to weight the measurement residual. If you recall, the measurement residual is the difference between the actual measurement and the predicted measurement. Once we have that weighted residual, we'll use that to increment or update the state estimate. It will turn out that the Kalman gain can be used to update the estimation uncertainty, which is also officially known as the estimation error covariance. Very often, however, we just use the term covariance itself. So let's present the mathematical formulation of the problem. And this is the general nonlinear time invariant discrete time formulation. So our variable k represents a discrete time or discrete time increments. The state dynamics model has the state vector x at time step k being equal to whatever, a function of whatever it was at time step k minus 1, plus some disturbance or process noise, w at time k. So k indicates the time step. It's not the actual time. The actual time at that time step is something like t sub k. And the time increment, the delta time between 2 time steps, would be then something like tk minus t sub k minus 1. And of course, x is a state vector. and it changes with time, so it's indexed by k. F is in general, nonlinear dynamics function that causes the state to change over time. And the WK is a process noise vector. So the measurement model is also a vector process. We have Z, which represents the measurement itself at time k. And then a general function could be a nonlinear function, H, of the state, plus some measurement noise, which is due solely to processes within the sensors. So Z is the measurement, H is a measurement function, and V is the measurement noise. So our goal, once we have this mathematical formulation, is to find an optimal gain K, capital K, that allows us to update our state estimate in the following way. As we saw in the running average example, we want our new estimate of K, of X at time step K, is F applied to the old estimate at time K minus 1, plus the gain multiplied by the measurement residual, which is the difference between the measurement and the predicted measurement, which in turn is H applied to F, which is applied to the state at time state estimate at time K minus 1. For now, we're going to ignore the update of the covariance matrix. That's something we'll talk about more in the next video. So the original Kalman filter solution actually only applied to linear models, and this is a limitation that we need to be cognizant of. Later we'll see how we can actually work with a full nonlinear model and with non-Gaussian noise and so forth. But for now we're going to focus on the original formulation, and it was subject to these limitations. So they're linear systems, so F has to be linear, and they're linear measurements, so H has to be linear as well. And the system and the measurements are driven by zero mean Gaussian white noise processes. And that's for both the process and the measurement noise. So from now on, we're going to assume that the function F is actually a linear vector valued function, i.e. it's a matrix, and we're going to call it phi because that has been traditional in Kalman filter theory practice. H is also a linear vector value function, so it's essentially a matrix, and that's common to use the H as the measurement matrix. So the problem then is to find a gain matrix K such that, just reformulating using phi and capital H, we've got this recursive update equation. Now we're going to declutter that in a second here because it's not really quite telling us exactly what we want to know. So once we get to the linear discrete formulation, we can say, all right, we've got a state dynamics model, linear one, driven by phi and the white noise for the process. So X is the state vector, phi is the state transition matrix, and W is the process noise. The measurement model looks something like this. Z at time step K equals H times the state vector plus additive white noise, V. And the goal is to find a state estimate in the form as follows. So phi hat at time step K is just, so not phi hat, X hat at time step K is equal to phi times X hat at time step K minus 1 plus the gain weighting the residual. So we're going to simplify the notation a little bit here, and this is very common usage as well. The term phi of X hat, operating on X hat, is actually the extrapolated state estimate prior to making the measurement update. So it's the predicted measurement. So to distinguish, I'm sorry, not the predicted measurement, but the predicted state. So to distinguish between the prior estimate and the updated estimate, we're going to use some notation as follows. So x hat with a superscript minus is going to represent the predicted estimate prior to the update. And the way you compute that is you apply phi to the prior post updated term from the prior time step. So x hat plus at time step k will be the updated state estimate. And in that previous expression for the predicted estimate, you'll see we have an x hat plus, but at time step k minus 1. So once we apply phi to that, we get a predicted estimate. That's why we use the superscript minus for that. And for an updated estimate, we use the superscript plus. So applying h then to the x hat minus will yield the predicted measurement. So putting all this together, the solution we seek should look like this. X hat plus should be x hat minus plus the gain times the measurement residual, which is z minus h times x hat minus. Okay. So you'll probably realize that this looks a lot like a running average problem. That was something that I was stressing in the first playlist. We'll remind you of that from time to time. All right, so let's summarize where we are. We formulated the linear discrete problem. We've indicated the form of the solution, the recursive estimating algorithm with the Kalman gain. But we haven't yet presented the complete solution because for a complete solution, we're going to need to compute the gain k. We know we have to use it, but how do you compute it, right? And we have to then use it to update the state estimate and also to update the estimation uncertainty or the covariance. So what's next? In our next video, we're going to drill down on the state dynamics some more and determine how estimation uncertainty changes over time and how it is updated. We're going to be applying the phi matrix to the estimation uncertainty or covariance, but we're also going to have to take into account the measurement or the process noise statistics, and that will bring in another matrix. So we'll have a matrix equation for updating the estimation uncertainty, or I should say for extrapolating the estimation uncertainty. And then we'll compute the gain and use that gain to update the measurement or the estimation uncertainty. All right, and that'll do it for this video. We'll see you in the next.